Here we discuss about a project, FPGA IP Core for DC motor control with adaptive neural network PID tuning and high-resolution encoder interface. Here, PID controllers are widely used in industrial and embedded control applications such as motor drives, temperature regulation, robotics, and process control due to their simple structure, inherent stability, and reliable performance. However, most conventional PID implementations are designed and optimized for a single specific system, often using software-based platforms or fixed hardware architectures. This approach limits real-time performance, scalability, and hardware-level verification, particularly in applications that demand deterministic timing and parallel processing. In this work, a general adaptive digital PID controller is implemented using Verilog HDL and realized on an FPGA platform. The effectiveness of the proposed controller is independently verified on two distinct control applications without integrating them into a single system. The first application is a BLDC motor control system, where the PID controller regulates motor speed and direction using encoder feedback and PWM control. The system is validated under multiple speed transitions ranging from 5,000 to 60,000 RPM, including directional changes. The second application is a temperature control system where a fixed set temperature is initially defined and the PID controller dynamically adjusts compressor operation based on sensor feedback to maintain the desired temperature. The temperature response shows smooth convergence from room temperature and maintains the set point within a narrow variation range. The key novelty of this work lies in demonstrating the adaptability and reliability of an FPGA-based PID controller through separate hardware implementations and functional verification across two fundamentally different control applications. Both designs are verified using ModelSim, and the resulting waveforms and response graphs confirm stable operation and accurate control behavior, highlighting the suitability of FPGA-based PID controllers for real-time and high-performance control applications. Now we can verify the paper. This paper presents FPGA IP Core for DC motor control system. As for this paper, we design an adaptive PID controller. The same adaptive PID controller design will used in temperature control system. Figure 1 shows the FPGA-based DC motor control architecture, where the adaptive PID controller, PWM module, and encoder interface are implemented as a single hardware IP. The incremental encoder provides real-time feedback to the PID controller, which generates the control signal for the PWM module. The PWM output drives the motor through an external motor drive circuit, forming a closed-loop control system. Figure 3 presents the hardware-level breakdown of the digital PID algorithm for FPGA implementation. The current error and its delayed versions are used with proportional, integral, and derivative gains to compute the control output through adders, multipliers, and shift operations. The final PID output is generated in 2's complement form, ensuring efficient and accurate hardware realization. The figure 7 and 8 shows the encoder interface operates by decoding the quadrature encoder signals using a finite state machine to accurately determine both speed and direction with separate state transitions for clockwise and counterclockwise rotation. Based on the measured encoder feedback, the PID controller generates a control value that is compared with a high-speed counter to produce the PWM signal. The PWM output maintains a fixed switching frequency while varying the duty cycle according to the PID output, enabling precise motor speed control. This work we have done in Verilog HDL, functional verification done in ModelSim, and we synthesized this work in Xilinx Vertex 5 FPGA and proved the performance in comparison table. This is the Verilog HDL coding for DC motor control system. Here we create separate coding for encoder interface, adaptive PID controller, and PWM generation. This is the simulation results for DC motor control system. Here we operate this DC motor control system in two directions, via left and right. Additionally, we operate this DC motor control system at different RPM level of 5,000 to 60,000, each present with different pulse rate and same 10 kHz frequency range. Next, work is temperature control system. This is the Verilog HDL code for temperature control system. Here, we operate this temperature with support of verification-based temperature sensor with compressor module. Here also, same PID controller encoder interface will used. The PWM generator output will given to the compressor to switch on the compressor and control the increment and decrement frequency range. This is the simulation result for temperature system. Here, verify the output of compressor PWM, compressor control, temperature increment, temperature decrement, and the sensor output will plotted in waveform. Initial temperature we set at 100 degrees Celsius. This controller will help to reduce the temperature in 1 by 1 Celsius, and it will maintain in set temperature range of 25 degrees Celsius. Next, we done the synthesize of this work. This is synthesize report for DC motor control system. Here, you can verify the logic size. This is RTL schematic. Next, this is synthesize report of temperature control system. Here, you can verify the logic size, and this is the RTL schematic. This analysis we done in comparion table. This is the final report of this work. It will present with title, base paper abstract, objective, proposed title, proposed abstract, general notes with advantages and disadvantages, finally, literature survey. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication, affordable project packages with ongoing support, customization to match your research needs, early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.